So, hello everyone, and welcome to this fourth JPEG NFT and fake media workshop. We have two speakers today, and after the two presentations, we have an open discussion and ask questions to the speaker. Before we listen to the speakers of today, I will give a quick introduction with some background about what has been leading to the organization of this this workshop. So let me tell you about some of the JPEG activities about fake media and NFT, and some of the common challenges and issues between these two activities. So first of all, it's important to stress that within JPEG, we have a whole range of standards. Most of them are image coding standards. But in addition to that, there's also some system level or imaging ecosystem level standards, such as GP search and JPEG systems that includes privacy and security, the metadata file format, and so on. But in addition to the standards that we have, we also have some explorations, and these are studies where we investigate a specific domain to see whether there is a need for standardization. And at this moment, there are 3 of these explorations going on. So DNA, NFT, and fake media. So during this workshop, we will focus on NFT and fake media, and in particular on the common challenges. So in standardization, and in particular for the explorations, we always start with engaging with stakeholders, and from this engagement, like we do with these workshops, we try to collect use cases, and from these use cases, we extract requirements. And then in the end, if you have a stable version of these use cases and requirements, we make a decision whether we issue a call for proposals. Now, looking at these two activities, NFT and fake media, with JPEG fake media, we're actually very close to releasing a call for proposals. With JPEG NFT, we're a little bit earlier in the process, and we're still investigating what the challenges are, and what the use cases are, and what the requirements are. So first, a few words about fake media. First thing I want to illustrate is that media manipulation in general is not something new. You can see a lot of examples here over the history with examples of manipulated media. But especially recently, thanks to deep fake technology, it has become much easier to create manipulated media, and also it became much more difficult to distinguish between authentic media and manipulated media. And of course, there's a big impact at various levels, both political, societal, and economically. Especially recently, we hear about media that's popping up every day, where it's very hard to trace back where it comes from and whether it's actually real or not. But there's also another side. So the same technologies that are used for manipulation can also be used in a creative way for modifying media. For example, for colorization, for denoising, for making super resolution images, or also for content productions. There's a few examples given here where actors can play 2 different roles when they were young and when they were old, thanks to the same deepfake technology. So within JPEG fake media, the scope is a creation of a standard that can facilitate the secure and reliable annotation of media creation and modifications. And while doing that, we shall support both the good faith use cases as those with malicious intent. So that's important to stress. While it's called fake media, we definitely focus on these two aspects of it. So as I said, we're called to issuing a call for proposals. So we have quite an extensive set of use cases. Again, here you can see that we have them both in the misinformation and disinformation side as on the media creation side. And on the JPEG website, you can find our latest document where you can find all the detailed descriptions of these use cases. In terms of requirements, we have 3 sets of requirements. The first one is related to the creation and modification description. So that's basically the metadata to describe the origin and all the modifications that have been applied to media assets. Then we have a set of requirements related to the embedding and referencing. So how do you link the metadata with the actual media content? And then finally, we have a set of requirements which are related to the authenticity, the integrity, and the trust model. And here again, so the whole list of requirements you can find in the latest version of our document. Now, looking at NFT, I think most who are attending this workshop are familiar with NFT, but basically NFTs, non-fungible tokens, provide a digital version of non-fungible physical assets in the real world. So in the real world, you can trade a painting, for example, and with NFT that brings that notion to the digital world, just like cryptocurrencies did for financial transactions. And it uses that same decentralized architecture, just like cryptocurrencies, so based on blockchain technology. Now, just like fake media, this is a hot topic at the moment. In 2021, there was a 2 billion market in NFTs, and here are a few of the famous examples of NFTs that have been traded. But in addition to the traditional examples, there's also like twins or replicas from digital to physical or the other way around. And there's also examples of like virtual objects like these sneakers, for example, which do not actually exist in the real world, but that can be traded as NFTs. There are, however, a lot of challenges involved with NFTs, one of them being the lack of interoperability, but also in terms of viability, reliability, security, and also in terms of the legal framework. So these are some of the challenges, and within JPEG NFT at the moment we're also working on a document that again you can find on the JPEG website, where we're trying to identify these and investigate what possibly could be done in terms of standardization to improve that situation. Now, this is a joint workshop between the two activities because there are clearly some synergies. So first of all, if you invest in an NFT, then obviously you're also interested in the trustworthiness of the asset that you're investing in. Also in the other direction, so NFTs relying on the blockchain technology, they provide an immutable record of a media transaction. And also in terms of media provenance, we're looking in these immutable records of modifications that have been made to media. A lot of this is related to metadata. How do you embed the metadata? How do you reference it? A lot of the metadata that is needed for the both is common. So that's an overlap as well. And then finally, and most importantly for this workshop, we also identified that the identification of assets and also of the actors involved is quite crucial for both activities, and there are some specific technologies like perceptual hashes and visual media descriptors that can play can or may play a role in this challenge. And this was basically the idea for this workshop, to look a little bit deeper in these technologies and see if we can draw some conclusions on the role that these technologies could play for fake media and for NFT. So that's it for my introduction. So here you can find an overview of the context of the people involved in these two activities. And again, on the jpeg.org website, you can find all the relevant information. So now we'll move to the first presentation. For practical reasons, this is a pre-recorded presentation by Neil, who is actually also present. So if you have questions, Neil will be able to answer them during the discussion session at the end of this workshop. So I'm going to share the video, and then we can listen to the presentation of Neil.
Hi, this is Neil Krawitz, and this talk is on applied hashes, both perceptual and cryptographic, and how they can be incorporated into image provenance and NFT technologies. In this presentation, I'm going to cover a little about my background. Then I'll focus on perceptual hashes, cryptographic hashes, how they work, and how they are different. Finally, I'll give some examples for using them with provenance and NFTs. As I mentioned, my name is Neil Krawitz. My company, Hacker Factor, focuses on research and development for networking, security, and forensics. Among other things, I write the Hacker Factor blog and run the photo forensics web service for digital photo analysis. I also run a search by image service called Routabout, which uses perceptual hashes to find pictures from the Internet Archive. When people hear the word hashes, they usually think about cryptographic hashes, which are used to tell if two files are the same. Perceptual hashes are a different concept. They are used to compare based on similarity. For pictures, they can find variations of the same image. And for audio and video, they can identify similar segments or clips. To help explain these differences, I'm going to go back to the basic definition of a hash and how they relate to random numbers, cryptography, and perceptual attributes. So what is a hash? In computer science, a hash refers to any kind of binning algorithm. This is like a first pass rough cut at sorting data. It's used to segment data by attributes. When sorting data, there is no real limit to the number of available bins. There could be dozens, hundreds, or even millions of bins for hashing or grouping the data. It really comes down to the number of desired bins and the specified binning algorithm. Sometimes you want to bin by specific attributes. However, sometimes, like with cryptographic hashes, you just want consistent groupings of data, even if the groups are randomly selected. An easy way to randomly group data is to use a random number generator as the hash function. A random number generator is an algorithm that generates a sequence of unpredictable numbers. Regardless of the specific random number system, every random number generator has the same basic configuration. There's an algorithm that mixes numbers and an internal state with a number for mixing. Each time you call the random number generator, it loads the internal state and mixes up the bits. Some of the mixed bits are used for the output value, and some are used to update the internal state. A simple random number generator works great at producing a pseudo-random number sequence. However, if someone knows the algorithm and has enough output data, then they may be able to determine the internal state and predict the next output value. More complicated random number generators watch for input that is unrelated to the internal state. This could be things like keyboard timings, when packets arrive over the network, or disk I/O transfer rates. Each time this external data, or entropy, is received, it updates the internal state. This way, someone who knows the algorithm cannot predict the next random value, even if they have lots of previous values. Cryptographic hash algorithms work like random number generators. Each uses a well-known mixing algorithm and a specific initial state. The data being hashed is used as external entropy and updates the internal state. After all of the data is processed, the final state generates the hash's value. There are lots of different cryptographic hash algorithms. Most differ by the complexity of the internal mixing system and the size of the final hashed output. For example, MD5 uses a relatively small mixing system and generates 128 bits or 16 bytes of output. SHA-1 is more complicated and generates a 160-bit or 20-byte hash value. And SHA-256 is even more complicated and generates a 256-bit hash value. As an example, I have a file called Bored Ape. Although the file extension is .img, the contents are in an image format called WebP. The file is 72K and it has a specific image size. This is not unique. You can have your own file with the same file name, format, size, and dimensions. However, I also generate some cryptographic hashes. If your file doesn't have the exact same cryptographic hashes as my file, then your file is not the same as mine. And if your file has the same cryptographic hashes, then we can be very confident that you have, byte for byte, the same file as me. With cryptographic hashes, the same input file always generates the same output sequence. If the files differ even by 1 bit, then the hashes will be different. If the hashes are the same, then they are likely bit for bit identical. With cryptographic hashes, there is no degree of similarity. They are either different or they are not. You may have noticed that I used the word likely. If two files have the same hashes, then they could be the same file. This is because hashes map large datasets into small signatures. While unlikely, it is possible for two different files to generate the same signature. When this happens, it's called a hash collision. To put this into perspective, MD5 generates a 128-bit or 16-byte hash value. An input file will map into one of these 16-byte values. This means that there is a 1 out of 2 to the 128th or 1 in 340 undecillion chance of having two different files with the same MD5 hash. Due to algorithmic weaknesses, it's actually more like 1 in 2 to 97th, but that's still a huge number. With odds like that, you're better off playing the lottery. MD5 is considered weak by today's standards. Other hash algorithms use more bits and more complicated algorithms for a lower chance of a collision. Perceptual hashes use a different binning concept. They don't use a random number generator. Instead, they group content based on attributes like how is the image colored, the location of colored transitions, also called gradients, or the location or orientation of edges. They can also focus on critical points or frequencies from signal analysis. These attributes can be global to the entire picture or local to specific regions in the picture. Just as there are lots of different cryptographic algorithms, there are lots of different perceptual hash algorithms. Many of these algorithms are field-specific. For example, astronomers take photos of the night sky and need some way to align similar photos of stars. One algorithm for doing this treats every star position as a critical point for alignment. As long as the stars are in the same relative positions, the images will match. Fingerprint matching uses a similar technology. The ridges define critical points for alignment. Locality-sensitive hashing is often used for matching similar text. A simple example of this is the common Unix diff program. In this example, I have two text files. One says, this is a test of text. The other says, this is another test of similar text. The diff program determined that the word a was replaced with another, and the word similar was inserted. Audio perceptual hashes, such as beat alignment, can be used to identify songs or audio clips. And algorithms like video barcode can be used to match video segments. For images, there are many different perceptual hashing systems, but most of them are proprietary. For example, Google's search by image system appears to be based on some kind of colored histogram and edge detection technology. Bing's image search is similar, but appears to be based on overall intensity. When I asked TinEye about their solution, they said it was magic, but it's likely based on critical point alignment. KarmaDK has indexed pictures from Reddit. They use a gradient hash system that I blogged about. My own root about system uses a set of global intensity gradients. In contrast, PhotoDNA, which is used for identifying child pornography, uses 36 sets of localized gradients. Most perceptual hash algorithms are not very complicated. For example, average hash, or aHash, uses a few simple steps to create and compare hashes. First, any borders around the content are cropped out. Second, the large image is reduced to 8 by 8 pixels. That's really small. The small image is converted to grayscale, and the average grayscale intensity is identified. Finally, the picture is converted to black and white, which represents the 0 and 1 bit values. Each bit indicates whether each of the 8 by 8 pixel intensities is above or below the average value. For comparing two hashes, you just need to count the number of bit differences. To demonstrate how this works, I'm going to use 3 pictures. The first is a JPEG that shows Kim Jong-un holding a DVD. The second is a PNG where someone replaced the DVD with an iPhone and closed his eyes. The third picture is a Bored Ape WebP file. For generating the aHash value, we first crop the images. The Kim Jong-un pictures removed the white border at the top and the black border at the bottom. The Bored Ape removed borders from the sides and top. Then the pictures are scaled down to 8 by 8 pixels. This removes almost all of the details from the pictures. The small image is converted to grayscale, and then the average color is determined. The image is finally reduced to black and white based on whether the grayscale intensity is above or below the average intensity. The black and white image has 8 pixels per row, and there are 8 bits in a byte. We can directly convert each row into a bit sequence. For example, the first row is white, 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 black, black, white, white, white. That translates to bits as 111001111, which is the byte value E7. We do this conversion to each of the 8 rows. This byte sequence is the perceptual hash of the image. To compare hashes, we simply count the number of bits that changed. For example, E to F is a 1-bit change. 7 to 7 has no bit changes, and C to D is a 1-bit change. The 2 Kim Jong-un pictures differ by 2 out of 64 bits, or 3% of the total hash. In contrast, the Bored Ape differs from Kim Jong-un by 35 out of 64 bits, or 55% of the total hash. Now we can algorithmically determine that the 2 Kim Jong-un pictures are visually similar, but not identical, while the Bored Ape picture is very different. Using this, we can determine a threshold or a cutoff level to detect visually similar pictures. Independent. The file can be a JPEG, PNG, WebP, or any other kind of image format, since the algorithm looks at the rendered pixels and not the file's encoding. aHash is also padding resistant, since any border around the image is removed. And aHash is aspect ratio independent, since it reduces the image to 8 by 8 pixels regardless of the aspect ratio. One of these pictures looks very elongated, but they both have the same perceptual hash value. Because aHash crushes the image down to 8 by 8 pixels and focuses on the average grayscale intensity, you can crop as much as 1/16 of the image from any edge without significantly changing the hash value. Similarly, recoloring the picture a little may change a few bits in the hash, but most of the aHash value will remain the same. And small edits won't make large changes to the aHash value. This makes aHash resistant to minor edits. aHash is an example of a very simple perceptual hash algorithm, but it works pretty well. Different pictures should have different average color intensity distributions. However, there are lots of alternative perceptual hash algorithms. For example, dHash focuses on adjacent pixel gradients. The black-white conversion determines whether the pixel on the left is brighter or darker than the pixel on the right. With pictures, low frequencies determine structure and high frequencies provide details. pHash and wHash focus on the lowest frequencies in an image. Most perceptual hash algorithms are applied globally, evaluating the entire image. PhotoDNA focuses on local gradients in an overlapping grid. Another option uses scale invariant feature transforms, or SIFT, to identify and align critical points. Even among these algorithms, there are implementation variations. For example, aHash, dHash, and pHash use 8 by 8 pixels to create 64-bit hashes. However, they can be easily extended to use 16 by 16 pixels for 256-bit hashes, 24 by 24 pixels for 576-bit hashes, or larger. Larger hashes generally means larger resolution for edit detection. As an example, I submitted the Bored Ape picture to TinEye and immediately found 310 results. However, the results spanned a variety of Bored Ape images. TinEye focuses on features, and all of the pictures have similar base features. Fortunately, Perceptual Hashes permit sorting the results by similarity. When sorted by most similar, the first picture that TinEye listed was a little darker than my submission. The next pictures had similar coloring, but different borders and cropping. And yet, they are visually variants of the same picture. As another example, I searched for the cover of the book titled Abraham Lincoln using my Roundabout search system. Roundabout found 10 variants of the image. Some have different dimensions, and some show the same book in a different language. Roundabout associates each picture with meta information. Besides finding the different variants of the picture, you can also find each collection at the Internet Archive that contains each picture. Just as cryptographic hashes can have collisions, perceptual hashes can also have collisions. However, with perceptual hashes, the collision is not based on the number of bits. Instead, it's based on the likelihood of having similar attributes. For example, the coronavirus, a dinner plate, and the Japanese flag all appear similar under aHash. Regardless of the perceptual hash algorithm, low detailed images will all appear similar. Every picture of a white wall looks the same, and every picture of a UFO in the night sky looks similar. The likelihood of a perceptual hash collision is dependent on the algorithm and the threshold for determining similarity. Depending on those choices, all of these Bored Apes could be similar, or they could all be different. There are a couple of approaches for resolving collisions. First, you can use different algorithms. Different algorithms evaluate different attributes. Second, you can use different bit lengths. If the 64-bit aHash algorithm isn't sensitive enough, then maybe try 256 bits. And third, you can adjust the threshold for determining when two pictures match. The great thing here is that you have lots of options. You can tune the perceptual hash for your specific problem space. Now that you understand how hashes work, we can start to address privacy. Hashes are often used when you don't want the server to store the actual data. As long as the hashes match, that's often enough to confirm a relationship with the source data. For example, cryptographic hashes are generated using a random mix, so they cannot be mapped back to the input data. This makes them a great option for storing passwords. As long as the entered password generates the same hash, you can assume that the user entered the correct password. And if the user's password doesn't generate the same hash, then you know that they didn't enter the correct password. If someone were to compromise the server and take the password file, then they would have hashes and not the actual passwords. In order to find the user's password, they would need to crack the hash. Brute force cracking tries every password combination, but since there are billions of combinations and computing each hash takes time, this is usually not a practical approach. Most attacks iterate through a list of common words and variant patterns, such as appending numbers or replacing certain characters. Unlike cryptographic hashes, perceptual hashes have a property called projection. With perceptual hashes, every bit For example, aHash maps a small black and white picture into bits. By the same means, the bits can be easily used to recreate the black and white picture. The 256-bit version of aHash contains more bits. It can be used to project a 16 by 16 pixel image. More bits means the projected image has higher resolution. pHash stores bits that represent the lowest frequencies in the picture. This may look like blobs to a person, but to the computer, different images result in different blobs. In general, fewer bits result in less projected resolution. You won't get a recognizable image from a hash that stores 64 or even 256 bits. In contrast, PhotoDNA uses 144 bytes to store overlapping gradient information. That's 1,152 bits, which means it can project into a much higher resolution image. A picture projected from PhotoDNA appears as a blurry grayscale version that is 26 by 26 pixels. That's about the size of a small desktop icon, and it has enough detail to identify the picture's content. When it comes to selecting hashes, people often ask for the best. However, there is often no best choice. With cryptographic hashes, the general rule is that more bits is better. SHA-1 is longer than MD5, so SHA-1 is better than MD5. SHA-256 is longer than SHA-1, so SHA-256 is better than SHA-1, and so on. The biggest trade-off is data storage, readability, and computation speed. Longer hashes typically take more computation time, need more storage space, and are not human readable. With perceptual hashes, the general rule is that more bits provide more resolution. Depending on what you're comparing, you may not want a high-resolution hash. In addition, different hashes measure different things. Depending on the media you are indexing, you may prefer gradients over colors or frequencies instead of gradients. In general, there is no generic better. There's only better for your specific needs. Now that we know how hashes work, we can focus on how they can be used with provenance and NFT technologies. Provenance provides information about the media, such as where it came from, how it was altered, and who performed the alterations. There are different proposed implementations. In general, they include a list of identifiers, actions, claims, and digital signatures. The unique identifiers can be generated using cryptographic hashes or random values, like a universally unique identifier or UUID. The digital signatures and tamper detection codes can be generated using cryptographic hashes. Most provenance solutions attach the information to the media as metadata. However, many tools and services, including Twitter and Facebook, strip out metadata. So what happens if someone removes the metadata? If this happens, then we could use a perceptual hash to find the media's provenance information. For example, we could generate a perceptual hash from the media and provide it to a signing authority. The signer could use the perceptual hash to search all of their holdings and then return a list of similar media and provenance information. This does introduce a few problems. These include having too many options, concerns about privacy and compatibility, proprietary solutions, and a requirement for trust. For example, different signers and services handle different content. We should expect different services to use different perceptual hashes. And we cannot expect signers to generate every possible perceptual hash for all of their holdings. Will users generate the hash or download a service-specific module? It's often easier to upload the media to the service and let them generate the hash. But sharing the media brings up privacy. Sometimes you can't provide the media to the signer due to the content, legal restrictions, or a need to protect the source's identity. With all of these options, we're certain to have compatibility issues, such as which media formats are supported. For pictures, JPEG and PNG are common, but what about Apple's HEC or Android's AVIF? If you need to download the hash system, then which platforms are supported, and what are the minimum system requirements? If the algorithm is proprietary, then you can't share the hashing system with the end user. This brings up the issue of trust. If I have to download and run a hashing module, then how do I know it doesn't contain a virus or spyware? Will there be requirements for DRM or heavily obfuscated code? If I have to upload content, then the service needs to expect hostile images, such as JPEG files that intentionally crash the JPEG library. And if I have to upload, how do I know that the service won't retain my private content? The applicability to NFT services is very similar. Every NFT provider has their own complicated architecture. These are heavily dependent on cryptographic hashes for identifiers, signatures, and validation. Most are also based on blockchain technologies, which are heavily dependent on cryptographic solutions. An NFT is a pointer to some media. But how do we map the media back to an NFT entry? What if the media is converted to a different format? Then we cannot depend on cryptographic identifiers. Also, how do we find out if the media is registered at multiple NFT services, or even if it is registered at all? One solution is to use perceptual hashes. As with the provenance problem, you can generate a perceptual hash and then have the NFT service scan all of their holdings. This has the same trade-offs as before, such as which perceptual hash to use, privacy for shared media, proprietary hash algorithms, compatibility, and trust. To wrap up this talk, I provided a brief overview of cryptographic and perceptual hashes, including how they work, hash collisions, and reversibility. Finally, I showed how they are applicable to provenance and NFT technologies. Again, my name is Neil Krawitz, my company is HackerFactor, and I thank you for your time.
So thanks a lot, Neil, for this presentation. We'll first listen to the second presentation from John Colomos, and then after that presentation, we'll open the discussion session So, John, the floor is yours.
Thank you very much. I will just share my screen. Just give me 1 moment. Okay, I hope you can see my slides. Okay, great. Thanks, Frederick. Okay, well, thank you very much for the invitation to speak. I'm at the University of Surrey, where I lead a research centre at the intersection of AI and blockchain. And I'm also a principal scientist at Adobe Research. And I'm going to be presenting today a bunch of research, actually 4 research papers, a summary of those in the area of content fingerprinting for image attribution. And this is very closely aligned to the area of perceptual hashing that Neil's just given a really excellent introduction to. So yeah, let's get started. So I guess certainly within today's audience, it won't have escaped anyone's notice that you know, hardly a day goes by without some kind of teachable moment in the press in terms of fake media and misinformation. Here are just a few examples from the last quarter of 2021. And many of these stories that you see, these fake stories, rely on synthetic or partially manipulated media being circulated. But in many cases, perhaps even most cases, the media is not necessarily manipulated, but it's been misattributed to tell a different story. And this problem spans multiple media forms: images, videos, text, audio. If we had a way to help users better understand where media, like an image, had come from and what had been done to it, then we could help those users make better trust decisions about that media when they encounter it online. In other words, what would be great is a set of tools that would help us establish the provenance of media. And this is very much the approach that our research has taken, and this is research that's been in collaboration also with the Adobe-led Content Authenticity Initiative, the CAI, and is relevant therefore also to the technical working group, the C2PA, that has been spun up by CAI, the Project Origin folks, and others. And that's not to say there aren't other perspectives on this problem, of tackling fake news and misinformation. I mean, detection of digital manipulation, for example, using image statistics or visual artifact detection, is an important part of this solution space too. But our work and the work at Adobe and the CAI and at the University of Surrey, where we've been collaborating, has been around this idea of establishing provenance and to enable content attributions to enable users to make better trust decisions themselves, be more informed about those decisions, rather than, say, making some AI-based classifier to detect manipulations and make authenticity decisions for them. So today's talk then is about content fingerprinting and its role in helping solve this provenance problem. And I'm going to ground that discussion in the Content Authenticity Initiative and the technical specification that is being developed by people in that initiative and others that is all about establishing provenance. And actually, we saw this briefly mentioned in Neil's talk as well. This idea of the C2PA is basically a standard. It's a technical specification, I should say, that is emerging to embed provenance data, what's called a manifest, into the metadata of assets, like, for example, an image. And the challenge there is, of course, that as that, let's say, image is passed around online, is redistributed online, it may pass through non-compliant or legacy pipelines in that distribution channel that will strip that metadata out. It may even encounter individuals or actors that intentionally strip that metadata out and may want to even substitute that metadata for alternative metadata to present an alternative false story to the provenance of that image. So the idea then is to use computer vision AI technology in order to match an image that has been stripped of its metadata back to some authoritative database of that provenance information containing that manifest. So we can imagine that a creator of an image might opt in to storing a copy of this provenance information, this manifest, in the cloud, or maybe even some form of distributed ledger. And then when a consumer encounters that image that's been stripped of its metadata, they can nevertheless establish a lookup and retrieve that metadata, and so recover the manifest and be able to then make an informed trust decision about that content. So the creation flow would look something like this. Let's suppose that a creator creates an asset. They might then use, for example, the content credentials feature, let's say in Photoshop or some other implementation of the C2PA standard to embed a secure metadata trail within the image. And then that image may then be published online. But at the same time, they might opt in to the storage of that metadata, that manifest, within a database. It might be in the cloud of an implementer, or it might perhaps even be in some form of decentralized file system, or perhaps even in a cloud store that's underwritten in some way by. And then when the image has circulated online, it may be presented in a form where it has no metadata, even, perhaps it might even have alternative metadata inserted into it. Nevertheless, a fingerprint can be created from the pixels in that image and used to look up the manifest and present then the results of that lookup to the user for validation, and optionally also perhaps visualize any areas of content manipulation within that image. And the crucial thing here is that that image may not only have had its metadata stripped, but also that image may have undergone any number of benign transformations online. So for example, resolution changes, quality changes, format changes that don't necessarily change the editorial content of the image, but they do nevertheless change the bits of the image which would render a standard or cryptographic hash unusable for this matching purpose. So there are two technologies then in this workflow. We call the content fingerprinting, which is effectively a way of doing a robust near duplicate image search. And then this ability to visualize the results and highlight any manipulation in the content. So I'll first go into a little bit of detail about how the technologies that we've been exploring for content fingerprinting work. I'll first of all show a quick video demo of this. I'm going to talk over this video so that we can see. So let's suppose that we encounter this image here of the president on Twitter, and we want to know if that image is an authentic image. And what we're doing here is dropping that image into our content fingerprinting system, and you can see that it's made a partial match. It's matched that image to an original image that has not been manipulated, and you can see with the slider here, it's also been able to highlight the area of manipulation in that image. In this example, we're dropping an image that has not been manipulated into the system. It's an identical match. You've got the green tick there. But here, in this case, the image had an ice cream kind of photoshopped in place of the light ones. And it's been able to highlight the area of manipulation. Now, in this image here, the image has been manipulated to swap the glasses from the girl to the llama. And you can see that the visualization tool is able to ignore the noise and other forms of benign transformation, but correctly identify the areas of digital manipulation. So the technology also works for video. You can see here in the top left, there's an original image. In the top right, there's an image that's been manipulated, but also subject to noise. And you saw a bunch of highlights where that manipulation had taken place. This final demo is showing an image that was basically fed into this verify site from social media, and it had no metadata in it because it had been downloaded from social media, but dropped into the content fingerprinting system. It's able to match to the correct provenance record and display that metadata nevertheless. So how does this work then? Well, the fingerprinting system is based on what we call a scene graph. So what we're using is computer vision to isolate the salient objects in the scene and then create a digital fingerprint of the content, the pixels of those objects, which we then feed into a neural network to ultimately create a hash of that image, a perceptual hash, if you like, of that image. But this hash has particular properties We want it to be robust to benign manipulation of the image, but we want it to be able to identify areas of the image that have been manipulated to change its editorial content. So the way that we do this is we train this neural network, and we describe the details of this approach in an ICCV paper last year called OscarNet. And the idea is we basically create this scene graph by identifying these salient objects. We visually fingerprint each object. We take note also of the relative geometry of those objects in the image. And then we basically feed those that graph representation through an AI construct called a transformer, which basically compresses that information down ultimately into a bit string. And the idea is that bit string does not change if the image has been subject to noise or other forms of benign manipulation, but does change if the image is tampered, and we can identify how much it's changed. So to give some examples of retrieved results, this is a corpus of 150 million images that are on the Behance website, which is a website of creative content. It's quite diverse in its artistic content in terms of, there's vector art, there's paintings, there's photographs, there's all sorts of different media there. And on the left, you can see a query that has been subjected to some benign transformation, in some cases quite serious quality degradation, and then the top one match that comes back from those 150 million images on the right. And you can see some similar results here from Adobe stock of a similar size corpus. So how well does this technique work? Well, actually, again, referencing the prior talk that Neil gave on the different kinds of classical perceptual hashing algorithms like aHash, pHash, and so on. These are the kinds of algorithms where computer vision researchers over the years have come up with kind of signal processing approaches to create a digest from an image, a hash from an image. And these tend to be outperformed by more contemporary AI-based approaches, like, for example, HashNet, DSH. These are basically training a deep neural network to create that hash from images. And we've been exploring data sets like the public PS Battles data set, which is basically a data set of photoshopped images to help train and benchmark some of these models. And we've seen that our approach, which basically takes a scene graph approach, an object-centric approach to creating the hash, that's our OscarNet approach, outperforms these other kinds of algorithms, classical, deep learning-based, that try to create a hash from all of the pixels in the image, the whole image in one go, rather than paying attention to a breakdown of the salient objects and composition of the image. As I say, more detail on that in the associated paper. The other technology is this image comparator technology, which basically is comparing the query image and its top one match, and attempting to highlight areas that are different due to manipulation of the content, but it wants to also ignore areas that are different due to these benign or non-editorial transformations. So the technology, you can see some examples here on the right. Basically, we've got an area here, we've got an original image, we've got a manipulated image here in the top left, and then on the right, we have the heat map that's been generated. And the heat map here that's been generated is in blue, and the ground truth is in green. And you can see there's a very close correlation between the prediction and the ground truth. And even if the image is subjected to benign manipulation, like, for example, a minor warping here and also some blur, it's still able to generate the same heat map. And we presented this technology in the CVPR workshop on media forensics last year. One of the other aspects of this neural network that does this image comparator is it also gives a sort of a classification output where it can give a kind of three-way classification indicating whether the images, that is the query and the matched image, are the same image subject to some benign transformation. Potentially they are the same image but subject to some manipulation, so editorial change, or they're completely different images. And that not only helps us give an indicator to the user to weigh in their trust decision on the content, but it also gives us a way to actually perform a second stage re-ranking of our top results. So a way that we found this to scale over many hundreds of millions of images is to take the top n results, where n might be 30, 100, something small and relative to the size of the corpus, and then re-rank those top results based on the output of this image comparator model. And in most cases, that leads to a good bump in performance. We talk about the details again and the specific numbers in that paper. Now, one issue in taking this kind of contemporary approach to perceptual hashing, if you like, rather than these sort of more classical approaches, is that they are machine learning based and subject to something called adversarial attacks. So an adversarial attack on an ML algorithm, machine learning algorithm, is most commonly encountered in the image classification literature, where, for example, you can show a neural network a photo of a cat, and by subtly manipulating pixels, perhaps even to the extent that you can't even perceive that manipulation as a human, it can nevertheless cause quite a significant change in prediction by a neural network. So it might, for example, turn the cat into a dog from the view of the neural network, but actually to a human, you'd barely be able to tell difference in the image. Now, it turns out that last year, it was shown that actually this kind of manipulation can also affect reverse image search and hashing algorithms as well from neural networks. And so we've just had a paper accepted into this year's workshop on media forensics at CVPR 2022, presenting a technique for training these hashing networks, such as our hashing networks, to be resistant to this kind of adversarial attack. So you can see here a workflow where you might have an original image subjected to some editorial change, but then the attack here would be that an attacker might introduce some imperceptible noise that nevertheless makes that image hash back to a non-manipulated image, an original image, or indeed might make it hash to a completely different image. And we can defend against those circumstances. The last thing I want to show by way of the image demo is a quick prototype that we've been exploring using a feature that shipped in the beta version of Photoshop at Adobe Max last year. It's called Content Credentials. And this is the service that actually embeds within the image the C2PA metadata that we've been discussing. So in this demo, I just want to rewind it actually, because I think it's gone a little bit ahead of time. Let me go back again. In this demo, what we can see is an image here being exported with these content credentials. Anyone can do this. It's got a beta version of this feature enabled in their Creative Cloud subscription. It will export the image with this content credentials, and that image is being dragged into the Content Authenticity Initiative's Verify site. And you can see inside that site a breakdown of the provenance information that's been embedded into that image. Now, if we take that image now and we post it on social media, so in this case, it's Twitter, and we save that image by dragging it out onto the desktop. If we drop that image back into the Verify site, because it's traveled through a tool that is not preserving that metadata, then actually that metadata would normally be stripped off. But what's happened here is, in the background, this content fingerprinting algorithm has been run and has been able to look up that provenance information and nevertheless then be able to present it to the user, even though the metadata for that asset was stripped. So I just want to close with a quick example of also this working in video. We've developed a network that leverages this image fingerprinting network along with another network which does audio fingerprinting to produce a video attribution solution along a similar line. So this system indexes 100K video clips. In this case, it's only short ones, 10 seconds or so, from a data set called Kinetics. And it performs robust audio and visual matching. Even matching here, as you can see, we've generated a query, just a fragment of a video, subjected it to some noise, and then you can see that in fact it's been able to find the correct video of those 100,000 videos, and it's highlighted the area of the video that is relevant to that query. So just bringing this back a little bit to NFTs, I think there's some really interesting intersection of this technology with the NFT space. If you think about what NFT offers, it's really about ownership provenance, and that's ownership in quotes, definitely. So who sold it, to whom and when. If you think about the sorts of provenance solution that technical specifications like C2PA are putting forward, it's all about creation provenance. So who made an image and how and when. And actually, if you put those two together, I think there's a really exciting route towards addressing this issue of misappropriation of IP and copy minting in the NFT space. So we've started to see some emerging solutions to this. So again, referencing the beta version of Photoshop that was released last year, there's a feature there called Prepare NFT, where you can sign into this C2PA metadata, the blockchain ID, if you've linked one with your Adobe account, that enables you to then demonstrate to several marketplaces that you are indeed the individual that created that asset, and when you mint it, and that can be matched, and it can therefore be flagged by those marketplaces if someone is minting an asset that they didn't originally create. The other thing that is I think an exciting area for these kinds of content fingerprinting technologies is the use of these technologies to resolve kind of copy paste attacks, where someone copies and pastes an NFT and therefore strips out its metadata. You could nevertheless resolve this C2PA information, which may potentially include things like the minting address being signed into that C2PA provenance trail, in order to establish whether you are indeed the originator of an NFT, and therefore should be the one that's putting it on the marketplace or not. So in conclusion then, I've just been demonstrating a couple of approaches to robust image fingerprinting that we've been exploring as a collaboration between the University of Surrey and Adobe Research. This kind of technology is useful in the context of what's referred to as a soft binding in C2PA and similar specifications, where we're not tying the metadata record directly to the image via cryptographic binding here. What we're using is effectively the content fingerprint as a backup, a recovery mechanism for when the metadata gets stripped, in order to robustly do an image similarity search on a trusted database in order to surface results. And that raises a number of design recommendations for the use of this kind of technology. One of them is that you should have a human in the loop to verify the results that come back from this service, because it is a near duplicate search. It may be the case that such technologies might surface non-relevant images, or perhaps may be forced to by some sort of adversarial attack, even if that risk can be mitigated. The other design consideration that's important to point out is that these sorts of services should be opt-in, not just in the storage of this provenance information, but also in the querying. It should be obvious to a user when these services are being queried for privacy reasons. There are a number of ongoing challenges for this technology, particularly in the video and audio fingerprinting space. The idea of how you can match temporal fragments over long sequences rather than short video clips and audio clips is still very much an area of research in the AI community. Also, the way that you can present these results back for human-in-the-loop verification. So thinking about a variant of the video summarization problem, where you want to highlight areas of manipulation when you consider the videos are temporal in their nature and also multimodal in their nature. They have audio as well. I think also, I pointed out some of the challenges in the NFT space around copy minting. I think content fingerprinting is a possible solution to that, but you do need to have recourse to some form of external source of truth, be that a cloud-based repository, or, in my view, ideally some form of federated or decentralized repository for this information, so that it isn't just a single organization that is effectively the source of truth for this provenance information. So I'll stop there, and I'm very happy to take questions in the open session at the end of the workshop. Thank you.
Thanks a lot, John, for your presentation. We'll stop the recording now, and then